So basically, the problem I'm going to talk about, or the research area I'm going to talk about, is kind of a new research area. Didn't exist 5 years ago, except for some few, I would say, introductory papers of the people who started to think about it. And today, if I'm looking on the field, we already have a worldwide conference that has around 150 people every year, and probably around 5 more conferences that have at least one session dedicated to this topic. And I'll talk about it and explain why this is needed and why it's kind of a challenging new area of research where many of the technologies that people talked about before maybe can be used. Probably there will be one new thing. I don't think I have even one equation in my talk. I hope it's okay. So first I would like to give credit. The group at the Technion, which is working on network-on-chip research, became a large group in the last 5 or 6 years. So it composed 6 principal investigators. 2 of them are from networking, Israel Cidon and Israel Kaslassi, myself. Actually, I still think we are the only networking people in the world working on network-on-chip. We couldn't convince others. Ran Genosar, who is a VLSI person. Avinoam Kolodny, who is basically a CAD and computer design, EDA, and a VLSI person. And Edith Kedar, which is a distributed system researcher. But who is really doing the work are, of course, the students. And this is just a list of students. Some of them already, I think, gone away. One even worked for for mayor. Actually, I'll mention the results that he got in this presentation. I would like also to give credit to all the partners, most of them from the industry. Along the year, we got financial support from many chip companies. I'll mention Qualcomm, Freescale, Siva, and Zoran, but in particular Intel, which is by far the largest contributor to our work. And Intel also and Freescale sponsor us in the Semiconductor Research Corporation, which is an American institute for research in semiconductors. And Qualcomm is actually the first implementer of our architecture. So in Qualcomm San Diego, right now they're working on chips that include some of the technologies that I'm going to show. So what is the problem you're trying to solve? So if somebody is looking on how chips are being built today, he will find there is some kind of art, I would say maybe black art, of taking these modules that are being designed by small teams in ASIC company, or let's say in Intel, where the teams are much larger, or Texas Instrument, and basically they are connecting these modules through technology we really know for years. One is a bus technology, right? Bus technology is really just a broadcast medium. Basically, you have a lot of lines. The number is increasing all the time. And some module is capturing these lines, transmitting a lot of information on them, and then releasing the bus for somebody else to use. While most of the traffic is going this way, sometimes because of timing problems and so on, people also have to make this spaghetti of basically point-to-point lines, okay? Because some modules need some critical signal to go to other modules and so on. So closely related modules should also connect like this. And what is a new paradigm? I'll explain why in a while, but first of all, what it is. So basically the idea is to take this, I would say, more or less chaotic world and transform it into a very elegant kind of communication mean, which we borrow from real networking, right? So basically, instead of having buses and spaghetti of lines, we're actually routing short lines, and I'll explain why short lines are much better than long lines. And we are putting routers among them. And basically, what we can have is communication between all these modules. And of course, there are multiple, what you can buy with a network is a couple of things. One is that you can have multiple communication going on at the same time, what you call spatial reuse, right? So this yellow module can talk to this module, blue module, and this red one to this green one concurrently. And in addition, we can multiplex a lot of the traffic together over lines and also get short lines between the routers. And each one of these properties is very important to what I'm going to explain in a minute. Okay, so what are the essential of this solution? So the essential of this solution is that basically each module needs to connect to the network using some standard interface. This is very important because today the industry kind of migrate modules from a design to another design. Right? So if you're working, I don't know, in TI and you built some nice module, in the next design you'd like to take your design and put it in the new design. So really we need standard interface. This is actually one of the problems of the bus. If you want to increase the speed of the bus and so on, sometimes you have to modify the interface. Actually, in the network, if you can see, the network can be faster and faster, but still one interface can be kept in a constant rate. So we don't need to upgrade it every time the network is becoming larger. We are switching from words communication over a bus to packet communication. I'll explain it in a minute. We are doing real routing through these micro routers. The traffic is being carried over these lines using statistical multiplexing. And statistical multiplexing is something which is very important in networking. You know, everybody that is taking my basic course in networking, immediately, you know, the first thing that I'm telling what is important about networks is statistical multiplexing. The fact that you can take all kind of bursts that need high peak rate, put them on one line. The probability that they will occur at the same time is very small. So I can basically build a fast line which accommodates more or less the average bandwidth and not the peak bandwidth of the sum of all the modules. Okay? So that's why statistical multiplexing is very important. Spatial reuse is the ability to concurrently send multiple pieces of information from different modules over the network. And something very important is that this whole network is not a new module. This whole network is automatically being designed by your design tools. And when you place the modules or when you create the modules and connect them together, the network is basically being compiled and automatically being placed by the design tools. So there is no one in the company that is called a network designer. Okay? This is the property of the design tools. Okay. Now, we claim that this is really a paradigm shift in the way the chips are going to be built. And if we are looking on other examples of past paradigm shifts, some of them, let's say, in the hardware world and one in the software world, they have some common, I would say, characteristic to them. For example, at some point, people stopped building like hardware-based final set machines and got one module which is called the microprocessor and built a lot of designs around this microprocessor. This was a paradigm shift in the way the chips were built. Another paradigm shift was going from schematic capture to logic synthesis, right? Actually, before the logic synthesis, basically the chip designer, where you're just drawing, gates and connecting them together and so on. At some point, they started to sit and become really programmers. Okay? It was a painful transition for people that didn't know how to program. But it enabled a new paradigm shift in the sense that new companies were built and design becoming available even for small companies. Now, object-oriented programming is another paradigm shift. If you look, my first research job was at IBM. When I was at IBM, I'm ashamed to say when, it was more than kind of 20 years ago, basically the productivity of a programmer was 2 lines of code per day. That's how IBM would kind of calculate when they put a team of programmers. And this was because these were COBOL programmers. It was very painful to test, to build, to program, and so on. Now, once people started to innovate and get new tools which are very efficient, today, if you look on, things which are fantastic, let's say suggesting Google and so on, they are actually built by very few programmers. And there was a paradigm shift in the productivity of programmers. So that's something that we want to do also in the chip design. Okay, so what are the characteristics of a successful paradigm shift? First, it solves critical market problem, and I'll talk about what is a critical market problem. Then there is a step up in the abstraction, right? Before the people you're using to draw finite state machine, then they started to program a microprocessor. They drew gates, and then they went to logic synthesis, and so on. So it's step up in the abstraction, and because of that in the productivity. But designers are affected. The old designers need a new way of thinking, and new tools, and they resist them. And also the design has these restrictions, right? People are saying, well, I like to write in assembly because I can have a control of my code. And if I write in Java, I don't. But, that's something you have to pay. At some point, you have to understand that you are giving some of the controls that you had before. So it starts with skepticism, and, at some point it's becoming standard, and we are kind of believing, research is much of a belief that this transition is starting to happen now. Oh, sorry. Okay. Okay, sorry. So these are the critical problems that the UNOC is trying to address. Okay? So what are the critical? First, I'm going to talk about the global interconnect problem. The problem is that long lines are becoming very inefficient in terms of delay, power, noise, stability, and reliability. I'll dedicate like 30 seconds to that. Number 2, I already discussed it, so it's clear. There is a system integration productivity problem, because it still takes the same time to build modules, even though modules are becoming bigger. But to interconnect the modules is taking more and more time of the designer. And today, if you look on modern chip, actually there is a nice article by Magen and Kolodny from our department that shows that already in Pentium 4, more than 50% of the power is spent by the interconnection, by long lines. And actually the system integration, that's also known, is taking more and more time for the designers. And the third thing that everybody is witnessing today is the emergence of chip multiprocessors. Right? We have the dual, and now we have the quad, and so on. And very fast we'll go to 8 and 16 and 64, and this also required this kind of solutions. Long lines. What's the problem with long lines? So, you are almost all probably electrical engineers, so I think it's very easy to explain it here. It's probably the best to explain it is using my hands. Okay? So, what was in the past? In the past, you have lines on the chip. They are kind of flat lines. They're very, distant from each other. So basically, you could route them and there was no problem. But when the technology starts to shrink, the lines are actually becoming high and becoming very, very close to each other. So, and they're becoming very thin. Now, what it means that they're becoming very thin? So R goes up, becoming, close. C goes up. RC goes up, power, delay, and so on, right? So the delays go, as the technology improves, the delays goes up, and the power consumption goes up. What happened to the single transistor? Actually, the single transistor, the gate delay, is going down. So what happened is that it's easier to work fast locally, and it's a nightmare to move information globally. Okay? So basically, buses that span the whole chip, or point-to-point lines, are just becoming a great bottleneck. That's actually what brought the chip multiprocessor into place. Because I cannot build anymore, on 1 centimeter square, a single chip, and operate it with a single clock. Another diagram that shows it is you look on the improvement in the clock speeds, right? The gate delay goes down, and you look on how far you can go in the chip in a single clock delay. So, when we were at 180 nanometer, we could actually have a single clock and cross the whole chip in one cycle. But when you are coming here, it's becoming impossible. Okay? So anyway, my buses are becoming very slow compared to what I need. My point-to-point line are becoming very inefficient, and I really need something, something new. So in 10 years, actually this slide is 5 years ago, at least, right? No, more, 7 years ago. They said that it will take 10 to 20 cycles to cross a chip. Okay. So now, let's try to do some calculation. I promise this is the only mathematical terms I'm going to use. Sorry? It's not equation. So basically, we compared in one of our work, what will be the area and the power consumption compared to the number to this square n. Let's say we have n modules. The chip size remains the same. It's always like 1 centimeter or 2 centimeters square, depends on the company. And we use this technique of point-to-point lines, just a bus and a segmented bus. Segmented bus allows you some spatial reuse, between the segments if you don't have global communication. And basically, you can see that the area of network on chip is the only one that grows linearly with the number of modules. Everything else goes at least, n square and a bit more. And if you look on the power, it looks less dramatic, right? Because here it's only n square root of n. But actually, if you look on the problem of chips today, it's actually more dramatic because the power problem is becoming much more dramatic than the area problem. Actually, people today don't know what to do with the area, but they, have real problems with power. Okay, so the new design basically, remember in the paradigm shift there was a new level of abstraction. So the new level of abstraction really means that instead of going from signal and bit communication, because that's what I'm doing in a chip, maybe I'm doing a word communication, I really go into what networking node to do the best. From message communication, I go down to packet communication. I'll explain what is a fleet communication and the fits of the physical units that I send over the links. I'll explain it in a minute. And what is more important is that I can get an abstraction of the communication requirements. Because basically what the designer is going to put into this design tool are just the requirements, right? He will have these modules. This is the inter-module communication. And then he have allowed latency for this communication, right? And the traffic rates that he needs from between the modules. He will take all this in one list, will put it into the automated design, and the network will actually will be built, and I'm going to show you how it's going to be built. Okay, that's a little bit of a history after we understand why it's a paradigm shift and what more or less is a network on chip. The first paper that was published, it's actually very, I would say, fast citing paper of Gourier and Grenier. Actually, nobody knows who they are. They published this paper. We invited them as keynote speaker in the first network on chip symposium. They never showed up, and I don't know. I never met them. They don't work on network on chip anymore. And then in 2001, there were only two or three papers, actually. One I didn't list. 3 papers. And I think most of the publications started in 2002. And probably when we entered into the area, there were maybe 40 papers or something like that already in the field. And I think there were something like 3 groups. The group of Demicheli from EPFL, and the group, probably know him, used to be in Stanford, and actually the group of Guzens from Philips, and I think that's it, basically. So, sorry, and the group from KTH. Okay, so first of all, if you are talking about the network on chip architecture, because that will be the rest of my talk, what is the architecture of network on chip? Right? I mean, that's kind of the $1 million question. And I think in a chapter, actually, I wrote with Guzens, we teamed together to write like a position paper, a position chapter in a book. We actually claimed that there is no silver bullet. One size doesn't fit all. In some sense, you have to optimize the network architecture to the type of the design that you are going to have. It's very bad news maybe for the tool makers and for the VLSI people because they need to learn more networking, but it's a great news for network designers and network researchers because we really hate TCP/IP and all the standards we have to live in, and we cannot change them anymore. So these are good news because if you look on the y-axis, what we are saying is that the design are very different in the way that what you know ahead of time about the chip. In ASIC design, or system on chip, you know exactly at the design time what will be the traffic of the chip. Because if you build a DVD, you have basically a high-level design. You understand exactly that from the DVD, you'll have to ship some block of memory to the MPEG decoder, and so on. So all basically the modes of operation are known ahead of time. On the other hand, there is this chip multiprocessor. Chip multiprocessors, I don't know, 2 dozens of multiprocessors or maybe 100, but they run programs. And since they run programs, I have no clue what kind of traffic is going to be in the system because it's a program dependent. And actually it's a mixture of many programs, right? So this will be a network on chip that will build to any arbitrary traffic, and it will be very hard to optimize. Well, this will be a very, very tight optimized design where I can actually almost get, the best design I can have. And in the middle, there are these 2 nice technologies. Probably one of them FPGA, because FPGA is exactly something in the middle. It's something that has infrastructure, but every time you program it, it has a known traffic, right? So it's becoming like a small system on chip. And SSP is actually very funded by Philips, where Guzen is coming from, which are application-specific signal processors. These are chips which are built as signal processor for many, many designs, okay? But they're not as general as CMP. So we'll start with the first paradigm, which is how you build a NOC for ASICs or for system on chip. And these are examples, right? The handset, that's exactly what Qualcomm will use inside our design. It will be a handset chip, a DVD, and so on. What are the requirements? So the traffic is defined at the design time. I know what the traffic is going to be. I don't need to build the chip in order to understand the traffic. That's very important. I can take it off simulations. I know what are the quality of service requirements, and I want automatic synthesis for that. What are the main optimization metrics? And what I really need to optimize is the power and the area of the network on chip. And this is new, because nobody built network before trying to optimize power and area. Usually you optimize link capacity, right, for BESEC or stuff like that. Okay, so at least here I'm presenting, there's actually more than one solution. Of course, I'm more focusing on our solution. But UNOC, which is basically the technology that I mentioned, which is now utilized by Qualcomm, is basically based on the following, I would say, characteristics. First of all, we understand the traffic requirements are known a priori. And the overall approach of building the network is to use very small buffers in the routers, to use wormhole switching. I'm going to explain what it is. To use quality of service in these links, so I will differentiate between traffic types and give different priority to different traffic type. I will use very, very naive or simple routing, which we call XY routing. And the topology, while it's a mesh topology, will be irregular because we permit different capacities for each link. And we'll use virtual channels. I'll try to explain everything in a minute. First of all, why XY routing? So XY routing has a couple of advantages. First of all, it's a shortest path routing. And remember that I explained to you about the power. If you go through the network, every time a packet goes through the network, it causes transition from 0 to 1. This is dynamic power consumption. And basically, as I want to minimize this number of transitions. So the best thing to do is to go shorter path for power. It actually creates a very simple router because all my routers are at most 5 ports, 4 for the neighbor and 1 for the module. The messages will go in order, so basically they all will go through the same route, and so they will arrive, one after the other. I will not need reordering, and yeah, I talked about short path. What is wormhole switching? Wormhole switching is a technique. And here comes a student who does the work. I mean, we have a PowerPoint implementation. I'll show you. Basically, the idea is that I take a long packet, I chop it into very small pieces, but these pieces go through the router one after the other. So only the first piece of the address, and the other pieces are just a byproduct. You understand, until you see the tail of the worm, you know that another fleet of the same size will come. So the pieces are called fleets. And if I want to go through this direction, that's basically what will happen. Okay, so the packet will go this way. What are virtual channels? Actually, let's go a little bit here. Since you can see that when a worm starts to go, it can capture many routers at the same time. And if the worm is very, very long, nobody actually can go into this path until this worm is over. Now, the idea of a virtual channel is that you build, it's like here, you don't have virtual channel. So this blue car, it wants to go left, but it has to wait to all the green cars. However, if you give it another lane, then basically it can overtake the green traffic and go directly to the left. Now, you don't need more bandwidth, right? You are still using the same bandwidth, but you are using actually different labeling for this blue fleet, so you can multiplex them in the same line. Okay? So this is how it goes in terms of the virtual channel. So on this link, I have two virtual channels. Let's say one is called 0, one is called 1. So basically, this router can differentiate between the flits coming from one of the preceding routers. Quality of service. We establish a quality of service mechanism in each router, and the idea is that you define priority class among the traffic of the chip. Now, what kind of traffic you see in the chip? For example, you can have a code fetch. A processor wants to go to the memory and bring code. This is very urgent, because if you do it, the processor will stop. Okay? You can have real-time stream, let's say MP3. You can have read-write or DMA block transfer. Now, these are low-priority things because they can wait, and this is a very high-priority thing. Okay? So we need to basically multiplex them and give priority to one over the other. And this is basically how UNOC looks like. It looks like there's buffers for virtual channel as for priorities. It has a crossbar switch, and it was implemented actually many, many times, especially by student projects, I think, maybe 50 implementations of UNOC in our VLSI lab. And how this design now is going. So what we built was a single router. Now we have to deploy a network. So how we design this network, assuming that we have these modules, right? And basically, we can extract all the communication information from these modules. Remember, these modules are software modules, right? They are just design modules. I can simulate them, and basically I can see how much traffic is going from each module to other module. Then, basically, the first thing I do is a placement. Right? So I place these modules and put them in such a way that, you know, the traffic or the power that is resulted by traffic is minimized. Now, this is very nice for networking people because, you know, I was never able, let's say, to put Jerusalem and put it between Haifa and Tel Aviv. Okay? That's not the type of optimization we can do, but you know, that's very nice in the network on chip area. Then what we do is we allocate, first we get rid of the links that we don't need, and we allocate link capacities. Okay? Because we calculate what kind of traffic we need. Now, basically, now I have to verify that my quality of service requirements are met, that each piece of message gets where it needs to get in the right timing, right? So it's the timing closure, and basically, you know, after if I missed something, then I have to add or reduce capacity from links, and basically iterate between these stages. Now, one of the problems here is that usually, if you are doing it using a simulation, it will take a long time because system-level simulation is very, very slow. So what we devised is that you iterate first, you are using an analytical model. So we built some analytical model of the delays that basically you suffer with this kind of traffic and so on. And only in the last stages you are applying real simulation. Okay? So you start with an analytical model and then move to simulation. And then if you look on one of the results that we kind of calculated, we get something like 30% saving in both the power and area of the node. Okay. Any question till now? Or?
How did you calculate the power and gain it that you had?
Well, we used only dynamic power, so it's easy. Dynamic power means that every time you switch between 0 and 1 or 1 to 0, you pay. So every time you go to a router, we know how many transitions on average it makes and so on. But that's usually what, at high level power is being captured. It's known that it's non-exact and there can be differences in the real chip and so on.
No, but actually what you say, you implement all the junctions
why.
A kind of buffer or something like that. And what seems to me strange a little bit is that you say it's more efficient than drawing a straight line.
I had a lot of fights here with all the networking people, right? Because networking people, what they like is what they are saying is the following. We have a network, and I have a traffic coming in. Now I need to route it in a way that it will load balance the links, right? So then I will take some of the traffic and take it away from the slow link and so on. But remember, here I know ahead of time what the traffic is going to be. So if I have a lot of traffic here, I put more capacity. I don't take the traffic away. I keep it in the link. So it's a much easier problem. By the way, when you build a network on chip for CMP, for chip multiprocessor, you cannot do it anymore because you don't know the traffic ahead of time. So the simplicity comes from the fact that I can simulate the whole system ahead of time, and when I build it, it's not going to change, right? It's not like the chip is not growing there, no more population is coming there, no modules are being built there, and so on.
So you're referring to the SoC.
Right. Yeah, it was the SoC.
But there's a lot of significance later to static power if you talk about cellular phones or something like that. We have a power consumption at static modes. Somewhere later on in your...
Well, these are more advanced work. We have also things about leakage. Okay, but I will not be able to cover it in in the time that is already going away. So, okay, let's go to the next thing, which is FPGA. Now, FPGA is like a very hybrid and strange thing, right? Because basically, what happened in FPGA, you get a chip. The chip is all the same chip, right? Now, you design something and you program it into the chip, right? And then this design stays there. It doesn't change anymore. Now, what you use in FPGA, right? FPGA is good for many designs, but each one of the design is static. Okay, now what are the features? That's something very important. So FPGA can be configurable to one of many applications. The traffic is known per application, right? But application may change. Now, usually what you have in FPGA is hard logic, things which are already there and you cannot change them. For example, today they would put a processor in the FPGA or a memory module or something like that, or a bus. And they have soft logic that you can change. Okay? And this soft logic is the one that actually gives you different applications for different chips. So our architecture of choice is really following exactly the same logic. What we are saying is that we know that hard logic is very efficient. Soft logic is not very efficient, right? Because it's programmable and it wastes more power, it takes more area. Now, what we do for the things which are constant, like links in the UNOC and so on, we are going to use hard logic. We're going to place them ahead of time. But we are going to use soft logic for things that we can program per application. So here we are abandoning the XY paradigm that you asked before. And here we basically are going to have to change the routing on the hard lines according to the applications that we have. Okay? And I'll give you just one example. So let's say that's a future FPGA. It's built of network on chip and configurable regions. That's like a today FPGA. There are also some functional unit like DSP or PowerPC or some processor. And the NOCs inside. Now, the infrastructure is laid out, but let's say the routing tables are soft. Okay? And also the network interface may be soft, because I'm not sure what kind of speed I want from every module. And then the example we took in one of the paper is that the only alteration you do in the routing, you route either XY or YX. Okay? And you can put every module in each one of these states. We really didn't want to put routing tables because they take a lot of space and power. And we kind of initiated what we called the weighted what, which is weighted XY routing. It means that each module can be either in XY or the YX. And we spread them according to the design. And basically, we run some simulation on some design of FPGA. And basically, we showed that this is much better, let's say, than fixed routes like XY. So it's not that this work is very important. It's more like the lesson. The lesson is probably from FPGA is that just like a design that is using the hard source resources over the chip and is using soft resources to have applications, also in the network you follow the same logic and you use the soft part of the network in order to follow the specific traffic patterns of this application. Okay, this is kind of the last thing. Sorry. NOCs for chip multiprocessors. So actually Intel is, of course, interested mostly in this kind of technology. And as we know, because of what I've shown before, the paradigm is that the next generation of processor is going to be chip multiprocessor because it's inefficient to build a single processor that run faster. Actually, as we understand now, it will run slower because of the long interconnection lines. And once you have chip multiprocessors, there is a paradigm shift in the way you have to program. You have to explore thread level parallelism and so on. And the question, of course, is how the interconnectors and network on chip will be built for this technology. This is an example of a possible chip, multiprocessor chip, that has, let's say, 8 processors and has a distributed cache, L2 cache inside. And actually, since this is like a coherent architecture, where basically all the caches have cache coherency, all the traffic really goes between the processors and the cache units. Now you have a distributed cache just to get spatial reuse, right? Because P0 can talk to this cache, at the same time P2 can talk to this cache and so on, so you get the acceleration. So design requirements, you have shared cache, we need to maintain cache coherency. The traffic is unknown completely. I have no clue what traffic is going to be. Actually, I need to retain some quality of service because I'll give you an example. When a processor goes to fetch something from the L2, it might be, let's say, is fetching a code word, right? It needs it in order to run. But processors are doing fetch, they're also doing prefetch, right? Maybe I'm taking this code and I need it only 20 cycles from now. Or I'm now issuing a request for a code word and I need it now. If I don't get it, I stop. These are completely different quality of service, and I need to distinguish between them. And this is architecture of choice. Actually, many people are starting to debate with each other because that's where adaptive routing is taking place, right? Maybe I need adaptive routing here. But the question if I'm still maintaining in-order delivery, because adaptive routing means that you change routes very fast, and some packets can go in different ways and arrive out of order, which makes your life very hard. Okay. Now, other features that you have to support very efficiently are like multicast features, right? Because if you have cache coherency, you have to submit sometimes multicast messages like invalidation, right? What I want to tell all the processors that some cache line here was invalidated because somebody wrote into it. So I need to issue a multicast command. Networks are not very good at multicasting. And maybe I'll skip it, so I'll be in time. And for that, we actually introduced a new architecture which has best of both worlds. We issue an architecture that has both a bus and a network. The bus is used only for what we call for very short commands and signal, and because of that, it doesn't need to be high bandwidth. It's actually a very low bandwidth bus, but it still has low latency. And the network on chip is basically running the high throughput tasks. So for example, if you are searching for a data line, you will search over the bus, but you send it back over the network, okay? Because the data line is much larger than the request. So this is what we call, this is a bus that connects all the module. It's in parallel to the NOC, and we called it BNOC, Bus Enhanced Network on Chip. And actually, this bus has very, very different features from the standard bus that you have on today's design. I think most of the chips today are using bus called AMBA, which has come from the company ARM, that has most of the processors. And BNOC actually has different bus. Again, I'll skip in order to meet the time. But we have a full design for the metabus. That's kind of the metabus design. And the metabus design is basically built mainly for power. And in order to build it for power, we actually have a masking mechanism that block the multicast operation if you don't need multicast. Okay? So it will have the power consumption of point-to-point when you submit point-to-point, and it will be very effective in multicast. Again, I'll skip it, even though the animation of the student is very nice. Okay, so that's kind of the flow. This is an implementation of metabus over a chip. Okay, of course, it's not a real chip, but we just took the same module over and over again and synthesized the metabus. And if you look on the results, you can see that if you look on broadcast results, basically you can see that the broadcast over metabus is much, much more efficient in terms of the latency than broadcast over the network. And of course, then broadcast over the network, which is here. But of course, that's something is wrong here. Metabus? No, sorry. Okay, that's metabus. Okay, this is the metabus broadcast. This is the point-to-point network unicast, and this is I don't know what happened here. The code line changed. So it's very efficient to do a unicast through the network. This is a metabus multicast, and this is a network multicast. I hope it's okay. And this is an example for applications that we run using the metabus. It's actually a real CMP simulation, and we show that using BNOC is much better, let's say, to use what we call the vanilla NOC. And these are real applications that parallel applications will run over CMP. And I'll skip here. And this kind of the last thing that I'm going to show, because somebody mentioned, when you go to CMP, you may want to use adaptive routing. Okay? Now, adaptive routing in a network and chip is a very costly thing. because you are not going to run a routing algorithm between the routers. The routers don't have processors, right? They don't send messages to each other and so on. So you cannot take the internet adaptive routing and try to map it somewhere here. So most of the people did the adaptive routing by the way that each router is only looking on the next router. And if this router is loaded, it either, let's say, go to the right or to down. For example, going shortest path to some destination. Okay? Unfortunately, if you only look on local information, you might have problems like the one depicted here. Because if I want to go from this corner to this corner, once I'm going maybe to a router which seems to be loaded, it's actually only medium congestion, this router will start to steer me down. At some point I will go again to this direction, but I don't know that ahead of me there is a very high congestion area. Okay? However, unlike real network, what we can do in network-on-chip networks is to have centralized adaptive mechanisms, and that's what we do in this work, which is actually was not even published yet. We're just writing it. But the animation is good, so I couldn't resist it. So this is what happens when you are doing only local adaptation. So somehow the packet stuck here, and because you didn't want to go through the yellow region because you didn't know, you didn't have global information. But if you are using the new algorithm, then basically you should calculate the cost of the whole path, and basically you reach happily the destination. Now, these are some simulation results where we compare. Dyad is a competitor written by other group, which is a local adaptive router. This is our result, still very fresh. Okay, but this is a circuit that actually take the global information from the network on chip and basically reduces it. If, let's say, you are starting from 16 by 16 network on chip, we're actually reducing the map into something which is maybe 8 by 8, and then we compute over this one what is the best path to take. Summary. Okay? So I hope I convinced at least the one who left, or who stayed, that network on chip is a paradigm shift in VLSI architecture. That network on chip is also a major research and industrial field. And as I said, in the last 5 years, probably the number of papers every year already doubled by 10 or 20. So there are many papers now being published. And there is already one startup that started to sell design tools. I think the investment was done there by Synopsys and ARM, which seems like the right companies to invest. Some design already appear in the market, usually for very large chip and very power-sensitive designs. NOC is not a miniature off-chip network. That's very important. You don't copy what you learned from internet or wide area networking and put it on chip, because first of all, there are major optimization factors, there are power and area, and both limit what you can do in the network on chip. You can solve the quality of service problem. You have problems like placement, routing, capacity, which are interchanged. The different network on chip architecture requires, which is very good for researchers. There are already maybe 20 or 30 designs in the market, and they're still growing. And of course, many new academic problems, maybe will be new NOC coding paradigms that can be established. Thank you.
We are slightly behind schedule. So if there's one question, we can take it. We'll take everything else offline. Is there any one question, or did you already ask the question that you want? So let's discuss these things online. Thank you again, Israel.